Hi, I'm Irene Maglasang Padilla, reporting about quantum mechanics. What is quantum mechanics? Quantum mechanics is a science dealing with the behavior of matter and light on the atomic and subatomic scales. It attempts to describe and account for the properties of molecules and atoms and their constituents, such as electrons, protons, neutrons, and other more esoteric particles such as quarks and gluons. These properties include the interaction of the particles with one another and with electromagnetic radiation, example light, X-rays, and gamma rays. The behavior of matter and radiation on the atomic scale often seems peculiar, and the consequences of quantum theory are accordingly difficult to understand and to believe. Its concept frequently conflict with common sense notions derived from observations of everyday world. There is no reason, however, why the behavior of the atomic world should conform to the familiar, large-scale world. It is important to realize that quantum mechanics is a branch of physics, and the business of physics is to describe and account for the way of world. On both the large and small scales, actually is not and how one imagines it or would like it to be. The study of quantum mechanics is rewarding for several reasons. First, it illustrates the essential methodology of physics. Second, it has been enormously successful in giving correct results in practically every situation to which it has been applied. There is, however, an intriguing paradox. In spite of the overwhelming practical success of quantum mechanics, the foundation of the subject contain unresolved problems, in particular problems concerning the nature of measurement. An essential feature of quantum mechanics is that it is generally impossible, even in principle, to measure a system without disturbing it. The detailed nature of this disturbance and the exact point at which it occurs and obscure are controversial. Thus, quantum mechanics attracted some of the ablest scientists of the 20th century, and they erected what is perhaps the finest intellectual edifice of the period. And now, we go to the article History of the Laws of Quantum Mechanics. Within a few short years, scientists developed a consistent theory of the atom that explained its fundamental structure and its interactions. Crucial to the development of the theory was new evidence indicating the light and matter have both wave and particle characteristics at the atomic and subatomic levels. Theoreticians had objected the fact that Bohr had used an ad hoc hybrid or classical Newtonian dynamics for the orbits and some quantum postulates to arrive the energy level of atomic electrons. The new theory ignored that the fact that electrons are particles and treated them as wave. By 1926, physicists had developed the law of quantum mechanics, also called wave mechanics. To explain atomic and subatomic phenomena, the duality between the wave and particle nature of light was highlighted by American physicist Arthur Holly Compton in X-ray scattering experiment conducted in year 1922. Compton sent a beam of X-rays through a target material and observed that a small part of the beam was deflected off to the sides at various angles. He found out that the scattered X-rays had no longer wavelengths than the original beam. The change could be explained only by assuming that the X-rays scattered from the electrons in the target as if the X-ray were particles with discrete amounts of energy and the momentum. When X-rays are scattered, their momentum is partially transferred to the electrons. The recoil electron takes some energy from an X-ray and as a result, the X-ray frequency is shifted. Both the discrete amount of momentum and the frequency shift of the light scattering are completely at variance with classical electromagnetic theory, but they are explained by Einstein's quantum formula.
This is Shanamiri Barbas and I am going to discuss about wave structure. So from 1900s to 1930, there was a revolution in the foundations of our understanding of lights and matter interactions. In 1900, Planck showed that light energy must be emitted and absorbed in discrete quanta to explain black body radiation. Then in 1905, Einstein showed that the energy of light is determined by its frequency, where E is equals to hf. So finally, in 1920s, de Broglie and Schrödinger introduced the concept of standing waves to explain this discrete frequency and energy states of light and matter. So standing waves only exist in discrete frequency and thus energy states. So it is clear that waves are central to quantum physics and our understanding of the structure and discrete energy states of matter, which explains why quantum theory is also called quantum waves mechanics. As we shall explain, the problems and absurdities of quantum theory have been caused by the continuing assumption of discrete particle concept for both light and matter, and thus the resulting paradox of particle or wave duality. As we are dealing with a scientific theory, it is necessary to begin by stating the central principles of the metaphysics of space and motion and the wave structure of matter, which describe how matter exists in space as a spherical standing wave and interacts with other matter in the space around it. From this foundation, we can then deduce the solutions to many problems currently found in quantum theory caused by this ancient concept that matter exists as particles. So principle 1, on what exists and its properties. One thing, space, infinite and eternal, exists as a wave medium and contains wave motions which propagate at the velocity of light. Matter exists as a spherical wave motions of space, which determines the size of our finite spherical universe with an infinite space. So principle 2, on the necessary connections between what exists. Any change in velocity of spherical in waves from one direction changes where these in waves meet at their respective wave center, which we see as the accelerated motion of the particle. This is the cause of all forces. So, for example, Newton's law of inertia. So the spherical in waves are formed from the Huygens combination of out waves from all other matters in our finite spherical universe. This is caused of Mach's principle, the mass energy density of space of an object is determined by all the other matter in the universe. So let us now explain and solve the many problems and paradoxes of quantum theory using the two principles of the metaphysics of space and motion and the spherical wave structure of matter. So during the years 1900s and 1930, many experiments were done on the interaction of light beams, particle beams, and metal targets. Analysis of these experiments showed that light and matter had both particle and wave properties. As we have said, the solution to this apparent paradox of the particle or wave duality is simply explain how the discrete particle properties, or quanta, are in fact caused by standing wave interactions. So to do this, we must begin by explaining the experimental foundations of quantum theory. Number 1, Max Planck's discovery of the particles, or quantum. Properties of light, E is equals to hf, 1900s. Number 2, de Broglie's discovery of the wave properties of electron interactions. Y is equals to h over mv, 1927. Number 3, the equivalence of energy, mass and frequency, and the Compton wavelength y of the electrons. Y is equals to h over mc is equals to 2.43 times 10 negative 12 m. So for example, the obvious solution to the paradox of the particle or wave duality of matter is to realize that the wave center of the spherical standing wave causes the observed particle effects of matter. Likewise, the discrete particle properties of light, quanta or photons, are caused by standing wave interactions, which only occur to discrete frequencies and thus energy states. So the difference of the two filters, this would be the result originally expected by Albert Einstein for the EPR experiment. And that would be all. Thank you.
Good day. By the way, my name is Janice P. Umboy. My topic is all about atomic structure. The atomic structure of an element refers to the constitution of its nucleus and the arrangement of the electrons around it. Primarily, the atomic structure of matter is made up of protons, electrons, and neutrons. The protons and neutrons make up the nucleus of the atom, which is surrounded by the electrons belonging to the atom. The atomic number of an element describes the total number of protons in its nucleus. Neutral atoms have equal numbers of protons and electrons. However, atoms may gain or lose electrons in order to increase their stability, and the resulting charged entity is called an ion. Atoms of different elements have different atomic structures because they contain different numbers of protons and electrons. This is the reason for the unique characteristics of different elements. Atomic models. In the 18th and 19th centuries, many scientists attempt to explain the structure of the atom with the help of atomic models. Each of these models had their own merits and demerits, and were pivotal to the development of the modern atomic model. The most notable contributions to the field were by the scientists such as John Dalton, G.G. Thomson, Ernest Rutherford, and Niels Bohr. Their ideas on the structures of the atom are discussed in this subsection. Dalton's atomic theory. The English chemist John Dalton suggested that all matter is made up of atoms, which were indivisible and indestructible. He also stated that all the atoms of an element were exactly the same, but the atoms of different elements differ in size and mass. Chemical reactions, according to Dalton's atomic theory, involve a rearrangement of atoms to form products. According to the postulates proposed by Dalton, the atomic structure comprises atoms, the smallest particle responsible for the chemical reactions to occur. So, the following are the postulates of his theory. First is, every matter is made up of atoms. Second is, atoms are indivisible. The third one is, specific elements have only one type of atoms in them. Fourth one is, each atom has its own constant mass that varies from element to element. The fifth one is, atoms undergo rearrangement during a chemical reaction. Last but not least, atoms can neither be created nor be destroyed but can be transformed from one to another. Dalton's atomic theory successfully explained the laws of chemical reactions, namely, the law of conservation of mass, law of constant properties, law of multiple proportions, and law of reciprocal proportions. So let's move on to demerits of Dalton's atomic theory. The theory was unable to explain the existence of isotopes. Nothing about the structure of atom was appropriately explained. Later, the scientists discovered particles inside the atom that proved the atoms are divisible. The discovery of particles inside atoms led to a better understanding of chemical species. These particles inside the atoms are called subatomic particles. So let's move on to Thomson's atomic model. The English chemist Sir Joseph John Thomson put forth his model describing the atomic structure in early 1990s. 17,588 times 10 to the power of 11 E-Bg. From this ratio, the charge of the electron was found by Mulliken through oil drop experiment. Conclusions. Based on conclusions from his cathedral experiment, Thomson described the atomic structure as positively charged sphere into which negatively charged electrons were embedded. Commonly referred to as a plum pudding model because it can be visualized as a plum pudding dish, where the pudding describes the positively charged atom and the plum pieces describe the electrons. Thomson's atomic structure described atoms as electrically neutral. The positive and negative charges were of equal magnitude. Limitations of Thomson's atomic structure. Thomson's atomic model does not clearly explain the stability of an atom. Also, further discoveries of other subatomic particles couldn't be placed inside his atomic model.
Good day everyone, this is the continuation of atomic structure. So, subatomic particles are the particles that constitute an atom. Generally, this term refers to protons, electrons, and neutrons. So, subatomic particles include electrons, the negatively charged, almost massless particles that nevertheless account for most of the size of the atom. And they include the behavior building blocks of the small but very dense nucleus of the atom, the positively charged protons, and the electrically neutral neutrons. So, atomic structure of isotopes. So, nucleons are the components of the nucleus of an atom. A nucleon can either be a proton or a neutron. Each element has a unique number of proton in it, so which is described by its unique atomic number. However, several atomic structures of an element can exist, which differ in a total number of nucleons. These variants of elements having a different nucleon number, also known as the mass number, are called isotopes of the element. Therefore, the isotope of an element have the same number of protons, but differ in the number of neutrons. The atomic structure of an isotope is described with the help of the chemical symbol of the element, the atomic number of the element, and the mass number of the isotope. For example, there exist three known naturally occurring isotopes of hydrogen, namely protium, deuterium, and tritium. The isotopes of an element vary in stability. The half-lives of isotopes also differ. However, they generally have similar chemical behavior, owing to the fact that they hold the same electronic structure. Atomic structure of some elements. So, the structure of an atom of an element can be simply represented via the total number of protons, electrons, and neutrons present in it. The atomic structure of a few elements are, first, hydrogen. The most abundant isotope of hydrogen on the planet Earth is protium. The atomic number and the mass number of this isotope are 1 and 1 respectively. So, the structure of the hydrogen atom, this implies that it contains 1 proton, 1 electron, and no neutrons. Total number of neutrons equals mass number minus atomic number. So the second one are the carbon. Carbon has 2 stable isotopes, 12 and 13. Of these isotopes, 12 has an abundance of 98.9%. It contains 6 protons, 6 electrons, and 6 neutrons. So the structure of carbon atom, the electrons are distributed into 2 shell and the outermost shell. For example, these are the valence shell, has 4 electrons. The tetravalency of carbon enables it to form a variety of chemical bonds with various elements. So, the third one are the oxygen. So, there exist 3 stable isotopes of oxygen, 180, 170, and 160. However, oxygen 16 is the most abundant isotope. Structure of oxygen atom, since the atomic number of this isotope is 8 and the mass number is 16, it contains of 8 protons and 8 neutrons. 6 out of the 8 electrons in an oxygen atom lie in the valence shell. So, from the theory of Bohr atomic theory, Niels Bohr put forth his model of the atom in the year 1915. So, this is the most widely used atomic model to describe the atomic structure of an element, which is based on Planck's theory of quantization. So, from this model or the theory, what are the shortcomings of Bohr atomic model? So, according to the atomic model, they vary in terms of the total number of the neutrons present in the nucleus of the atom, which is described by their nucleon number. So, that will be all. Thank you.